Thank you very much for the introduction and for the invitation as well. So it will be a bit of a change of pace here. I will talk about work on perceiving humans in 4D. This is not specific to the self-driving scenario, but I think this is a problem that is very important in this setting. So you want to be able to predict where a pedestrian will move in space, what their gestures mean or they want to indicate. You want to react quickly. If you see a kid running in front of the car in the street, you want to avoid collisions at all costs. So it's important for this setting how people move in the world, where they are, what they intend to do. These are all very crucial questions. So the way I'm studying the human perception of humans is in 4D, as I say. And what I mean with that is, let's see this unconstrained video where people can move freely. If I pose to a particular frame here, this effectively gives us a 2D observation of the world. Meanwhile, the true state of the world in this setting is, in this case, is 3D. So you see people that have 3D bodies and they can occlude each other. They can, some of them are closer, some of them are further away. And this extends similarly to video. In that case, the observation is 3D, X, Y, and T, so a spatiotemporal volume of pixels, whereas the true state of the world is 4D. So people have 3D bodies and they can move over time and in the space they have. So these are quintessential inverse problems that we're trying to solve, from an image to 3D, from a video to 4D. And we have been making a lot of progress in the last few years. So we can apply these methods for human reconstruction in the wild videos and get the pose of and shape of people. We can handle different poses, different viewpoints, even placing different people in the same coordinate frame, and do this in a coherent way. And the goal, of course, is to do this from any image possible. So, for example, if you give me an image of that includes some of my advisors, I want to be able to reconstruct this in 3D and be able to look at them from different viewpoints as well. And okay, in computer vision, we like to stand around posters. You will see a lot of us these days, but we really want to do more. We want to be able to capture poses and motions that go even beyond that. So our quest is really towards trying to capture any human motion. And this has been something that we are struggling with. So here, I will show you some results from our state-of-the-art models that we had roughly 2 years ago. So this model used to work well with very standard poses, but then the moment that you see something that is not very common in the training set, maybe an unusual pose or like unusual lighting, maybe more truncation, occlusion, this started failing. And this is not specific to this video. This is not cherry-picked. This is the most this is a known behavior of this model, or it used to be. Because we think that we have had the breakthrough here. So I will show you how, I'll show you the before and the after here. And on the left, you can see what our model from 2 years ago looked like. And on the right, you see the reconstruction we get with our most recent work. And here, we don't apply any temporal smoothing on either of these methods, specifically particularly on the right. There's no temporal smoothing. This is frame-by-frame processing. We are able to handle much more challenging motions. You see smooth reconstruction for the duration of the motion here. So how do we do that? This is part of our Humans in 4D paper. This is work that was led by Subham, jointly with Jathan, Angzu, and Jitendra. This work done at UC Berkeley. So this follows on this direction of human mess recovery. This is the very common way to address this problem in a feed-forward manner. So you have a single image of a person as input, then you have a network, this HMR network, that takes the image and estimates the parameters of a parametric model of the human body. So we have a simple parametric model of the human body, and this network regresses the parameters of this model for the person in the image, the pose, the shape, and the camera here. And you can pass these parameters to the parametric model and get a 3D reconstruction in the output, which you can rotate as well and see it from different viewpoints. This is pretty standard at this point. What we did with this next generation of systems of what we call HMR 2.0 is scale up when it comes to both the model we use here and the training data. These are the key, the two key ingredients here. And beyond that, we try to keep it as simple as possible. So for HMR 2.0, we go from this convolutional encoder to a fully transformerized design. So we adopt this VIT backbone that takes as input this tokenizes the image and takes the tokens as input, and after processing, gives these tokens to the transformer head that estimates the pose and the shape of the person in the image, and gives us the same 3D reconstruction as I showed you before. So very much same architecture, just we can scale it due to the properties of the transformers. We can scale it up much more compared to what we could do with convolutional networks. The other aspect is, of course, training data here. This is very important. You see here what we used to employ in this space. We had this a number, roughly 500,000 images, but most of those were in these studio settings. Now we actually go in the wild. We collect a large number of in the wild images, and we use a procedure for pseudo labeling these images. So first we detect the 2D key points of the person in the image, and then we fit the parametric model to the person in the image, such that the projection of this of the joints of the parametric model aligns with the 2D key points that we detect automatically on the image. So this gives us an order of magnitude more images, so roughly 5 million images with this pseudo ground truth, pseudo annotations. So I can show you how it works. I will keep some of these videos playing just to convince you about the robustness and the precision of our model. We tried it on videos from rhythmic gymnastics, or from artistic gymnastics. This is from skateboarding. And again, all these are per frame results, so no temporal smoothing is applied here. And we use a single model for all the experiments. We can do diving as well. So we tried it to really stress test this as much as possible. And here are some results. We tried it on skating, and this was one of our highlights here, because our advisor Jitendra has been working on this particular video sequence for almost 20 years. He has made students work on this sequence for almost 20 years. And this was the first case. The proof is in these papers. It was the first time that we could actually get this level of this quality of results in 3D for this particular video. So this is qualitative proof of how this system works. In terms of the quantitative performance, makes sense to use it to evaluate this method directly on the most popular 3D benchmark, 3D pose estimation benchmarks. And what we observed is that our model was marginally worse, or was performing the same as what these previous works were reporting in these benchmarks, which kind of worried us in the beginning. And then we started thinking how these benchmarks actually look like. So many of these data sets are actually taken, many of this data is collected in indoor settings with same participants doing the same actions in the same scene, or doing some very limited actions and motions in this space. So it makes sense for these previous works, and actually some of these previous works are training on these data sets as well, not on the test sequences, but on these similar settings. So makes sense to have this slightly more overfitting of the results when applied when we evaluate on these settings. And in fact, we're not so discouraged by this difference in the performance, because it was easy for us to get to improve the performance on this particular benchmark. So with yellow, you see a model that we trained that performs optimally on these benchmarks. But what we actually wanted to achieve was a robust model that would behave very well also on the in the wild case as well, that are the most challenging ones. And here is where our model actually shines. So when we evaluated on more diverse data, we could actually get a more consistent boost compared to previous work. Let me show you some more comparisons with this previous work. So on top right, you see results from our approach, and then on the bottom, we have previous state-of-the-art works. So our approach works consistently better in these settings. And the other way that we wanted to use this work was actually as a model that you could really apply and solve many downstream problems in this setting beyond just the estimating the pose of a person. And one way that we operationalized that was through the problem of tracking. So we addressed the tracking as 3D tracking. So from a video, we're getting the 3D reconstruction of the people, and then trying to solve for the association in this video. So getting this tracking the identities here, and this was done with 3D features, not with just 2D features. And again, we employed that to be able to both reconstruct and track people in the video. So keeping track of the identity here, even in these more challenging cases where there are occlusions, where one is might be occluding the other for a little bit, or even more extreme cases, as these wrestling videos here. And in general, yes, we did evaluate on the tracking setting as well. And the results we report are favorable compared to the state of the art, particularly, again, on more challenging cases. So this is just the summary on the tracking performance on the post-track dataset, and where our tracking method outperforms previous baselines, both 2D and 3D tracking systems. So this summarizes our 4D humans work. We have released the code, training code, testing code, the models. We have a hiding face demo, like a collab demo that you can try. All the code is on GitHub. So just go ahead and try it and see if you can break it. Actually, we're curious to see cases where this wouldn't work well. And if you are already working in this space, I believe that this could work very well as a drop-in replacement for what you might have already been using for pose estimation. So we're very happy with this, and particularly with these results. But we're still thinking that we were very far from actually having something that could solve this problem. And just to demonstrate one of the weaknesses that we had here, I want to show you this. Yes, so this video where we track people in this video, you see a little bit of jitter here. So this is not completely smooth. And things become even worse if you actually observe this from a novel viewpoint. So what you want to do when someone shows you this type of 3D results, you always want, from monocular input, you always want to observe this from a novel viewpoint as well. And here you see that the jitter in the results is much worse here. So you see people, although you know they are mostly static in the space, they can actually translate much more than what you expect. They are not in the same row as you expect from observing the video. And this is for a video with a static camera. If the camera is actually moving, things become much worse. You see people translating in space, and you get something that's completely incoherent here. And this is where our next work come into play. This is what we call SLAHMR for joint motion tracking, camera tracking, and motion reconstruction of humans in video. This is work led by Vicky together with Jitendra and Angzu again. And our main insight here is that when you watch a video like this one, you see the person running from left to right. That's what you perceive. Perceive this person actually running from left to right. But if you actually go in the pixel space of this image, you see the person being almost always at the center of this image. So if you didn't know that the camera was moving here, you wouldn't perceive the person as running in this space. You understand this because the camera, you perceive the camera also moving here. And this is a very standard problem of this pipeline. So you see how yes, again, for this video, the reconstruction that you could have with a standard system is what you get on the bottom left, where the person is actually running in place with a static camera. That's the only way to model the 3D scene. You assume that the person is running in place, the camera is static, and the person is not translating. Whereas what we actually perceive, I mean, this is very different from what we actually perceive. And what we perceive is what you see on the bottom right here. You actually see the person running from left to right, and the camera actually translating in space. So the main insight was to actually jointly model both the human and the camera motion here. And the details of how we do this is an optimization approach where we first take a video. Using the 4D humans work, we are able to get to track all the people in the video and get an initialization of their 3D poses. The key ingredient that is that hasn't been leveraged before here is tracking also the camera motion, and we do this with a SLAM system. We use Droid SLAM here primarily because of its robustness. So when we have both this 3D perception of the humans in the camera frame and the camera motion, we can actually pose this optimization problem and jointly solve for the coherent 4D reconstruction, which will take into consideration both the camera motion and the motion of the people in the space. So here, people are actually moving coherently in the 3D space. And as I said, this is an optimization approach. We have a number of objectives to optimize for this for its video separately, and the objectives are related to reprojection of the person in the image. So we want its 3D body to project where we expect them to be in the 3D space. We have some priors, pose priors, and say priors for the people in its frame, plus a number of plus a motion prior, so that the person is moving coherently in the 3D space over time. And finally, some environmental constraints. These are related to, with these, we want to avoid foot sliding, or we want to avoid the feet penetrating the ground here. So it's this, again, optimization approach that we optimize its video separately, and this can also be slower, unlike the 4D humans work, which does all the inference in a feed-forward manner. Now, for some of the results, I want to show you on the bottom, on the top right here, you can see the baseline that is not actually using the camera motion. So you see that the motion of the people in space is quite incoherent. The people never come close to each other. The baseline, the single frame baseline, is more coherent when it comes to relative position between the two people, but it's still very noisy. You can get the best of both worlds when you actually combine, or you actually use our approach that combines both the camera motion and the person motion in space. In terms of the results, we achieve a very strong performance. Again, on this setting of when we consider the global trajectory of the people in space, not just their local pose, but also how they move in space, how much space they covered in the video. Here is like our approach, SLAHMR, and yeah, we have these are results on the ego body dataset, and we consider two different metrics, both global position, global location error, and acceleration error. And let me show you some more results of this again, with challenging cases with This can work challenging cases with many people where there can be a lot of occlusions. You put the people coherently in the 3D space, which is actually what we need in many of these applications. We want to know exactly where each person is in the 3D space, not just infer their 3D pose. We want to know how much they moved and which direction they were heading. And we can also handle like more challenging cases with a bit more occlusion or more extreme camera motions and these unusual motions as well. And when you combine this with 4D humans, you are able to get both these smooth poses that I was showing you before for these sequences, both the smooth poses and the reasonable motion of the person in the 4D space, in the 3D space. So again, here, this is a case where the athlete is always at the center of the image, yet you can see actually how the person is translating in the space during the video. So this is our SLAHMR work. Again, we have the code and the demo available for you to use. This builds on top of the 4D humans work. So just go ahead and try it if this is relevant for your application. And I would like to briefly mention some of the other frontiers that we're pushing while we're dealing also with these problems. So another direction that I didn't cover is better human and scene reconstruction here. So we have work also in this direction where we'll try to jointly reconstruct the people and the scene from data coming from TV shows. With this pipeline that we're building, where we are both tracking and reconstructing people, you can extract even more attributes from these representations. Here, we use this for action recognition, where at every time frame or at every short snippet, we are also predicting the label of the action of the person, which can also be useful. And another attribute that we can extract from our representation. And then again, from other frontiers that are also aligning with CVPR, we have work that studies human-human interaction in close interaction. So considering also the contact of people, this is work led by Leah, and we present this on the poster session on Thursday morning. And these are cases where previous works are struggling a lot because you have very heavy occlusions, because they don't consider because they consider each person independently. So it's more common to have interpenetrations. Here we can model the contact more accurately. Something that could be interesting here is follow-up work that are actually trying to put this SLAHMR reconstruction into a simulation environment and being able to control each character separately, which will allow us to also inherit some of the advantages that the simulation environment can have. So maybe avoiding for free the collisions between the different characters, or avoiding sliding effects. So this is a work that is presented on Wednesday, and this was led by Nicholas. And finally, we are also, have work on building realistic avatars. I didn't touch on that either. We were mostly focusing on the perception problem, how to get an accurate 3D representation. On top of that, you can build another layer and have a better capture of the appearance of the person as well. And this is a poster that we're presenting on Friday morning. And with that, I would like to thank all the collaborators for these works. I'm very indebted to all of them and very grateful. And I would be happy to answer any question you might have. Thank you.